can't hear me. And you're about to hear double. Oh, good. Since I didn't play the music. Awesome. Trying to get some new Ethernet cables, seeing what we have going on, just hanging out, relaxing. How's everyone doing? We're out of coffee. Who's all here? I think I saw one person's watching so far. Maybe it's just me watching. Stats 1's watching Stats 1. If you were here, we're here to answer questions. So let us know. We're also here to buy Ethernet cords. What is the best Ethernet cord? So let's see here. Best Ethernet cable. We're going to get some new Ethernet cables. 10 best Ethernet cables for 2021. So they're saying Cat 8. I don't know the difference between Cat 7 and Cat 8. So they're saying Deblani. Let's go find this on Amazon over here. Look up a random article here. Does this exist? I don't see it. Maybe if you are here, feel free to say, hey, I'm going to maybe order an Ethernet cable. Hyperion Cat 8. I'm willing to pay some good money for a really good Ethernet cable. This one is Cat 8. What is the difference between Cat 7 versus Cat 8? What is the difference between those? What's the difference? Cat 7 cables, also known as Cat 7, Cat 8 cables. What does it mean? I've always seen that. If you're here, feel free to say, hey, we're broadcasting under it while Brian looks at Ethernet cables. Here's the details. Cat 7 cables offer performance up to 600 megahertz, where Cat 8 can offer 2000 megahertz. Whoa. So the cable alone could be limiting the bandwidth. The maximum cabling length of Cat 7 is 100 meters with 10 gigabits per second. But how's it? Where Cat 8 is 30-meter cable length with 25 gigabits or up to 40. If we consider pricing, Cat 8s are more expensive than other standard, considering its unique features. Cat 8. Cable construction. So the pros for Cat 8, the fastest copper network available for any distance. Due to different connectors, they are not compatible with Cat 5e and Cat 6 cables. So I think they'll work. So they're saying the fastest copper network available for any distance. So Cat 8. So is it copper? Is that what the C stands for? So we don't want that long of ones. Let's go right here. And if anyone joins in, I can't select cable length. Are those not available? That's weird. We'll see no one's appeared on stream yet as Brian is still looking at cables right here. I'm just broadcasting myself right now, trying to find better Ethernet cables. Maybe we're not even streaming. I think we are, right? Yeah, we are streaming. Join in if you have questions right now. A lot of people worked on the morning office hours. So here we go, Cat 8 Ethernet cable. Maybe we'll get someone who knows cables and stuff in here, and they'll be like, get this cable immediately. Here, let me get a little tiny cable because I need short cable going from the router to the modem. Oh, I hate these ones that have like 2 reviews. I never want to buy something that has 2 reviews on Amazon. Never, never, never. Oh man, it's hard to find the cable you want. There's about 1 billion cables to pick from, and someone's selling cable for $153. That's insane. Hey, Dylan, in assignment 9, do we have to make them all with all the indicators? I don't think so. I don't think you're making them all with all the indicators. Dylan, let's hop over and do that. I'm going to find this cable at another time. Did you already go over the hot dog nutrition question? We can do that, Jessica. You bet. We'll do Dylan's question right here. We're going to hop into it now. Brian was searching for some Ethernet cables. Which one are you talking about, Dylan? You don't have to make it with all the indicators. Let's hop over to the main screen. So which one were you talking about here for assignment 9, Dylan? Do we have to make a model with all the indicators? You don't have to make a model with all the indicators right here. Towards the end of this, you will be making a model with an indicator. Make a model predicting bill in USD by a party from the weekday. So you'll do weekday right here, and that'll be the variable you'll use to make predictions. Explain to the reader what day is missing from the output and why that day is missing. This is the only one where you're required to use indicators and explain the indicators. So the main portion of like what are indicators and how do they work are in this part of the assignment right here. Does that make sense, Dylan? So this is the only time you really have to use indicators, and you'll be going through putting an indicator in the model. You'll be explaining to the reader kind of the reference level idea right here. They can still create models in the earlier tasks that don't have indicators. In the earlier task 1 right here, there's 3 tasks actually. Let's look at task 1 right here. Task 1, make a simple linear model, just explaining from one variable right here, so you don't need to pick an indicator there. Make a multiple model, explaining tip percentage, and include the summary. So that was your email. Wait, what? They can still create models in the earlier tasks that don't have indicators. I think I'm so confused. The last sentence right there. Run a partial F to compare these models. So we're going to compare our simple to multiple model right here. Interpret the results of the partial F test so that someone who doesn't understand statistics can understand it. So the whole point of this one right here is the partial F test right here to interpret the difference between the simple to the multiple. So the goal is making a simple model, making a multiple model, and doing the partial F and interpreting those results right here. The next problem right here, create a new variable. So now we need to create a new variable to the data frame, which can be any sort of new variable we want to create. Add this variable to your multiple model from the previous problem. So whatever multiple model you created right here, which can be many, many different types of multiple models, as long as it's a multiple model. Down here, you will add the new variable to the multiple model, and then you will check the p-value and explain the significance in the multiple world. And then we get into some more indicator stuff. I missed that one. I'm a bit confused. You got it. I'll do it here next. Really, I'm being really semantic, like because you said the earlier tests didn't have to have indicators. I didn't know if you were implying the later tests. Yeah. Oh, well, so, yep. We got a lot of questions. Awesome. Make a model. This is where you have to have indicators, Dylan. So does this answer? You must use the indicators here. You can use them up higher, but you must use indicators here. For task 3, you will be doing indicators here. Task 2 is all about variable creation, and task 1 is all about partial F. So there's no real requirement to use indicators there. They can be used, but you're not required to use indicators. Can you go over from the quiz about if the interval would be large or small? Yeah, definitely, Julia. You got it. We've got Jessica's question, then we got Sydney's and Julia's. So let's do them. Is this all making sense right here, Dylan, with all these? A good 5 minutes to start. I use them because they're because of the weekday variable. Which part did you use where? You might want to send it to me or something. I don't know. I'm trying to think. I don't know which part where, and then the weekday variable. At the end, you are using weekday. I think maybe that's what we're talking about. You are using indicators right here because weekday is a categorical variable. So you will be doing indicator variables right there. So good stuff. Yep. Let's see. Jessica said the hot dog nutrition problem. You got it. Let's go check it out. Look at all those Ethernet cables over there. Ethernet cables. Okay. Hot dog nutrition problem. Let's go get the hot dog nutrition problem. Policies, close out. And Z tables. And Brian right there. Brian Inception. And hot dog nutrition problem. Okay, I think. Here we go. Here's the hot dog nutrition problem. I need your help, though. I need your help to complete this. Let's go ahead and take the variables right here. And what do we notice about the data on this? What do we have for this problem? The task 3 was the only part I was using. Yep, that's fine. Excellent work, Dylan. Great job. Yep, task 3 is the only one where it's required. What do we have notation-wise? I need help for the notation on this. Practice your notation. What do we have notation-wise right here? There's all the notation we need to identify for this problem. So what do we have notation-wise for this problem right here? Notation-wise, what do we have? I need some help with the notation. I'll go ahead and write the equation. So what do we have notation-wise? I need some help on the notation. Who has parts of the notation right here? So identify parts of these notation. Who can do it? What notation do we have here? The more you practice your notation and going through it and being like, okay, this means this. Hopefully, after a certain point, you're like, oh, that's that, that's that, that's that. You start seeing the notation and hearing it as you're reading the problem, which really helps with solving the problems pretty quickly when you identify what the notation is. So what notation do we have? Who can help with that? Mubot's already put the t-applet in the chat. The t-applet's going to help, especially when we get to this star right here. The star means you get to pick the t to a certain extent. It's based on the degrees of freedom. So I'll do one portion, but I need help with the rest of it. What else do we have right here? What else do we have right here? What is any of the other notation right here? The more you do it, the more like sometimes I look at it and I'm like, well, that's just obvious, but it's just because I've done this problem about 50 times. Nice job right there, Jessica. You are correct. Y hat is going to be this right here. Thank you, Jessica. And that's y hat, which is the sample mean. This is the sample standard deviation, and this is the sample size. It's important to note that these are like samples, so we have y hat instead of mu. Mu means the true mean, where y bar, I think I'm going to, y bar, so it's y bar technically. Y hat is the predicted y value, and y bar is the mean of the y, the mean of the sample. So when we put a hat on it, it means predicted, like from a regression equation, and the bar means the mean of the variable. But great job, Jessica. Let's throw out some 50 points. So the hat is predicted, and the bar is the bar means the mean of the variable. So this is the mean of the sample for variable y. So that's the sample mean of variable y from a sample size of 60. This is the sample standard deviation for the sample size of 60. And so now we need to go find this t right here, and we've got the t-applet. The t-applet is going to help us out. And one thing we did not mark on the problem is we did not mark the degrees of freedom. The degrees of freedom are going to be n-1 for this. So go here, degrees of freedom, and the degrees of freedom are n-1, and the degrees of freedom are thus 59. The degrees of freedom tell you which t you are using. There's infinite t distributions. All t distributions are like the normal, and the applet's in the chat right there. So the t is like the normal, and it'll become just like the normal with 1.96 eventually, with basically infinite degrees of freedom, or as it gets higher and higher and higher. But we are building a, I think, 95% confidence interval with 59 degrees of freedom. So let's go here. That is the right answer, but let's show it this way where it looks like a 95% confidence interval. So if it is 95% confidence, which I do think it is, let's find out. I copied it over to here. It is 95% confident, and that's what the star means. It means you need to pick the confidence level, or it'll be told to you in a problem on my Pearson, and that's going to be 2.001 right there. Let's double check our decimals, make sure we didn't. There it is, and that's that. So the y bar is going to be 323. And then we have here the standard deviation of 36 over the square root of 60. And now we're going to solve, and this will get us over on this side, this will get us the margin of error. So the margin of error for this problem is going to be 60 square root 36 divided by, that is now the standard error. We times that by 2.001. That is now the margin of error, 9.3. That's awesome. That really rounds to 9.3. We're just going to call that 9.3. And that means 323 plus 9.3. That is the interval, y bar plus or minus the margin of error, because everything right here solves to 9.3. So 323 plus or minus 9.3. And so let's do it. Copy, 323. Oh, 323 plus 9.3, 332.3, and it is one decimal. And 323 minus 313.7. There we go right there. Let's look at the assumptions. We would have to assume that the hot dog weights are independent, which basically means random, and that they're going to be normally distributed right here. Not one of my favorite questions that we ask, but this is basically random and independent. And then we assume they are a little bit normally distributed, which they do ask earlier or later on too. Is the randomization condition met? We don't know, but let's go ahead and assume. Don't love that question either. Is the 10% condition met? Yes, definitely, because 60 hot dogs is less than 10% of all hot dogs. So yes, 60 hot dogs is less than 10%. Is the nearly normal condition met? We don't know because we can't see the shape of the distribution. So we can't see if we have a large enough n right here to meet the nearly normal, but probably, because unless it's really skewed. Last but not least, we have to interpret the confidence interval. So we have a confidence interval interpretation right around here somewhere, where I am blank % confident that the true blank is contained in the interval blank to blank. I know I did it earlier today. Am I losing my mind? Maybe I am. Well, I'll be. I swear Here it is. I am blank % confident that the true blank is contained in the interval blank to blank. This is document 16, a very valuable one. I am 95% confident the true mean sodium content for these hot dogs is contained in the interval blank to blank. So we are 95% confident that the interval contains the true mean sodium content of these reduced fat hot dogs. Yes. Today we are on fire. We are getting nothing wrong today. The other question was, Sydney wants to know, I'm confused on the write-up for section 2 part D of the project. I can't tell if high casual demand is affected by weather or not. So let's look at section 2 part D on the project. Section 2 part D. Oh, we need to hop over here. I think I did a cut in the video, if I remember. So section 2 part D. Sydney, let's talk about that. You're welcome, Jessica. Great work. Thank you for helping out with the problem. I appreciate that. We're going to look at section 2 part D of the project right here. Let's head over and look at that. Here we go. Section 2 part D of the project, create a contingency table in a mosaic plot where we look at high casual demand and weather. In the contingency table, remove the total percent and column percent, take a screenshot of the mosaic plot, and contingency table, write a short conclusion on whether you think the high casual demand is affected by weather or not, looking at the row percentages to support your decision. So we're going to do something similar to this. I never worked the exact problems, but let's look at gender and breaking a bone. So we're going to go to Analyze, Fit Y by X right here to make the mosaic plot. And in this platform, you'll see down below, they'll show you what graphics you're going to make here. But we're going to take, this is kind of like your project, but we're going to take a categorical variable here. We're going to see if gender can explain why people are breaking bones. So we have here, and whether or not people break bones. So this is the data right here. Gender, does it explain why people break bones? Let's go ahead and click OK right here. And what do we notice? Well, let's make the table the way it should look by removing out the total percent and the column percent. And then I'm going to do something right here for my screenshot, which many people might not do, but if they're watching this, they might. I'm going to click this button right here. I'm going to click this one time, so I let go of it, and then I'm going to drag this over to right there where the long thing appears. And with that, I think I'm going to look at one thing real quick. With this, I've put everything side by side, and I can make this a little bit bigger. Let me go back to the arrow now. You have to go back to the arrow. And make this a little bigger. Awesome. So now when I screenshot this, I really like this as my screenshot for the project. I'm going to go right there. Did I catch the edge of that? Oh, I did. Technically, if you get a little too much, you can always crop the image, but that's got it. That's a great screenshot right there. That is everything side by side. Don't worry if it's not side by side, not the end of the world, but I really like this graphic right here. And let's take a moment to think about this graphic and what this graphic means while I look at one thing right here. Where's my camera green screen? There it is. And whoops, don't do that. What's this? Oh, that's the wire. A little bit of wire was getting on my nerves. Okay, so let's take a look right here and bring this over. What do you think about this right here and what's going on with this? Who can explain what this value right here means versus this value? Let's do the following. Really? Did I reverse it? No, I didn't reverse it. Yep, you are seeing it. Great job, Sydney, right there. When you look at this right here, here's the values connected to. So I'm trying to pick different colors, and great job. I'm trying to pick different colors so we can kind of look at these really. It chooses like the last color I have. I have tried updating Microsoft Word. I did that yesterday. It didn't fix the problem I keep having. Microsoft Word, what are you doing to me? So if you look at these percentages right here, these are the within male, within female percentages. So given someone is male, that's what you're reading across here with the row percentage, because the row percentage will go across the rows this way right here. So you're just going across the percentages right here, like given someone is male, given someone is female, what's the probability of this? What's the probability of this? And so especially looking at this, you would say that males are more likely to break bones than females. It's not saying females don't break bones, but given someone is male, the probability of them breaking a bone is 58.5%, where given someone is female, the probability of them breaking a bone is 48.6%. And you can see right there, there's the yes versus the yes for male. So right here, there's the yes for male, and here is the yes for female. And males are more likely than females by about 15% or so, 14.82%. And no. Yeah, 14.82. And so yeah, there's a sizable difference, a decent difference between the conditional distributions. Is that making sense? How to analyze what you'll be analyzing, Sydney? What we would say, so we wouldn't say gender is affected by breaking bones. We would say, and this is really good for here. Let's do something for the future. So this is going to future-proof us. The null hypothesis here, which we have not covered, first time doing this semester talking about this. And let's think about this, and we'll look at the p-value for this. This is not on the project, but this is good ideas right here. Gender is independent of breaking a bone. Alternative hypothesis. So gender, what would you say here? We'll look at a p-value for this in a moment. But you would say it looks like there is evidence, what? Just by looking at this, then I'll show you the p-value. But just by looking at this, would you say it looks like gender is independent of breaking a bone, or gender is not independent, which you could say dependent right here, or you could say associated. They'll say that on some of yours. Gender is associated with breaking a bone. So independent means they don't influence each other. Associated means they have some sort of dependency or non-independence. So this is a fine. I usually just like to write gender is independent, gender is not independent, or X is independent of Y. Yeah. So what does it look like right here? Does it look like that they're associated in some way, like gender is associated with breaking a bone? Like there's some sort of like associated. It looks like they're associated. It looks to me like gender is associated in some way with breaking a bone. It doesn't mean if you know someone's gender, you'll know they break a bone, but if you know someone's gender, you'd be like, oh yeah, males are more likely to break bones. Probably because like sports, contact sports and stuff like that. Of course, cheerleading, like super dangerous sport. Nothing wrong with cheerleading, but just, oh, that's a dangerous sport. Get thrown up in the air like 50 feet. I don't think they throw them 50 feet, but pretty crazy. We're not doing this for the project, but if you were to do it, the p-value is right down here. And look at the p-value. The p-value is low. So what do? You reject the null. So since the p-value is low, you reject the null. Couldn't it be argued both ways, though? Like breaking a bone is associated with gender? You can flip it. You can flip it by doing, if that's what you mean, you can just flip the X and the Y. Usually I put X is associated with Y or X is not associated with Y. So it would just flip the way it's viewed, but the p-value is going to be the same. So you could flip the analysis right here. It'll make the graphic look a bit different, but the mathematics will still be the same. So you could say X is independent of Y. Y is independent of X. Usually we like to say X is independent of Y. So whichever one we put in the X, like does gender explain why people break bones? So you always think like X is going to do the explaining. Does that make sense, Sydney? Like we ask, does gender influence, like explain why people break bones? Not, you could ask it though, which I wouldn't use it this way. Does breaking a bone explain someone's gender? Does that make sense? Which one goes in the X is the one that's doing the explaining. So asking it this way is, does breaking a bone explain why somebody has a certain gender? This way is, does somebody's gender explain if they break bones? So it'll do the same mathematics. The mathematics will be like, mathematics will do its own thing and work the same way. And both ways you get a p-value that is statistically significant, telling us that there is an association between these two variables. But since they are two separate things, they're both independent of each other. So wait, that is the null hypothesis. The null hypothesis, and this is for way later in the semester, like we've gone beyond the project right now. The null hypothesis is that they're independent, and then we're looking for evidence that they are like associated or not independent. So, so you can, the easiest way to remember it is like they're independent or they're not independent, but being not independent means associated. Like this right here means the same thing. So you could also write this. You could write it this way. There's quite a few ways to write this one, but the null is that they have nothing to do with each other, and the alternative is that they have something to do with each other. The reason I like to write the null the way we wrote it to begin with is because this is the chi-squared test of independence. So given this is the chi-squared test of independence, I always like to say, well, all you're going to do here for the null and alternative is you're going to write out that x is independent of y. And then you'll go right here for the alternative and write x is not. Does that make sense? So since it's the chi-squared test of independence, this is fine right here. And my Pearson will use this wording. My Pearson will say, like, it's not associated, it is associated, means the same thing. Like, not associated means they're independent, that they have no influence on each other. Sometimes people also write this one as dependent. So there's just many, many ways to do this. It's just they all mean the same thing when you get back to the idea of, you know, X has no influence on Y, X does have some sort of influence on Y. You know, gender, that's just the X variable. And if you switch them, it's fine. But really good questions. So all I do, especially when I tell students how to solve this, you'll see me do this during class, is I just tell everybody, when you see this graphic, like here, wait, I want you to try this. You ready, Sydney? I want you to write out the null hypothesis for what I'm about to show you. I'll show you the trick to write the null hypothesis for this. Whenever you see this right here, oh, and I bet you there'll be a difference here. Ooh, is there not a difference? Oh, it is. Yeah, I would have been shocked if there was not a difference. Okay. Somebody's what and what. The only thing you'll put between these, you bet, Emily, which one do you want to do? Which problem do you want to do? I think we had some more problems lined up. So let's start doing those here next. You got it. What is the only word you put between these? How would you write the null hypothesis for this? Try writing the null hypothesis for this right here. Oh, the rat one? Yeah, Julia. We'll do Julia's, then we'll do Emily's. You got it. So what is the null hypothesis for this? So when you see a mosaic plot, that's all you got to do right there. So all we got to do is get the null. Who can write the null hypothesis when you see this mosaic plots? Right here. And we do reject the null right here for this one. We think there's evidence that it's not this. So the null would be that they're independent. So that's the alternative. That would be the great job, Sydney, right there. That would be the alternative, is that they are associated, like somebody's distance from campus is associated with their relationship status. Like if you know someone's relationship status, like they're married or they're single or they're dating, then there would be some sort of like association between where they live. So the null is that they're independent, and the alternative is that is an association. Oh, definitely, Ansley, you got it. We got, I think it was Julia's, and then you got it for assignment 9. How do you create a new variable in R? Paige, we'll get to that here in a second. Yeah, let's do that. Sorry, Paige, I missed that one right there. Let's do that. We'll go do that here after 2 my Pearsons, then we'll do the 321. Let's do this. Julia said, can you go over about the interval larger or smaller? Yes, Julia, you got it. Let me put a break in the video. Yeah. Okay, let's go find that interval larger or smaller one. How does the question start? How does the question start, Julia? How does the larger or smaller interval one start? I do not know off the top of my head. How does the larger or smaller interval start? I'm trying to find it here as we go through. I have a guess of which one. I might do a step on here for a second. Let me see. The rat maze one. We might do the rat maze one real quick. Well, a medical researcher. Okay, cool. Thank you. Oh, found it. Let's do it. Here we go. I was literally on it. Okay. So a medical researcher is looking at the pulse rates right here of individuals, and they make a 95% confidence roll. They use the student T because Mr. T. Explain carefully what this interval means. When we do our interpretations, we always do the following. It's like document 16, I think. Look at that. I am blank % confident that the true blank is contained in the interval blank to blank. I am blank % confident that the true blank is contained in the interval blank to blank. We are close enough, 95% confident that the true mean pulse rate is contained in the interval blank to blank. They changed it up a little bit. They give the interval, and they do mention it that it's the true mean heart rate, and they give the confidence level. Look at this one right here. It's just a totally different way of doing it. No, none of this right here. No, no, no. I am 95% confident that the true mean pulse rate is contained in the interval blank to blank. Awesome. Now, when it comes to the margin of error, this is where people usually get stuck on this one with the margin of error. The margin of error is always what the length of the interval. No worries, Julia. The margin of error is always what the length of the interval. I love these as test questions. It's like, okay, we can ace these if we get them on the test. Like if we said an interval goes from 120 to 140, what would the margin of error be for this interval? What would the margin of error be for this interval? What would the margin of error be for this interval? And what is the margin of error? It'd be 10. Great job. So how did you get that? What did you do to get 10 for the margin of error? You are correct. An interval that goes from 120 to 140 has a margin of error of 10. So how can we get that? And just think about it like you would take the what of the interval and then do what to it. The margin of error is just what the length of the interval. Like if you have a length of the interval, there's the length of the interval. Exactly. So the margin of error is just half the length of the interval. So we take the distance the two numbers are apart, and then we divide by 2. So let's go ahead and take the distance these numbers are apart. So we're just going to take half the length of the interval right here. Half the length of the interval. Perfect. So half the length of the interval. The length of the interval is the distance the two numbers are apart. And now we're getting the distance the two numbers are apart. And then we divide by 2. There's half the length. We round up. And there we go right there. So that's half the length of the interval. We just did large number minus small number divided by 2. Half the length, half the distance. And if a researcher calculated 90% confidence interval, so 68, 95, 99.7, as you get more confident, the interval gets wider. That's not the answer to the question yet. But as you will get more confident, going from 68 to 95 to 99.7, the interval will get wider. So 68, 95, 99.7, your interval will always get wider as you go from like more confident, 68, 95, 99.7, 68, 95, 99.7. Your interval will get wider and wider and wider. Going from like a 68, which has a z-score of 1 about, which we're using t's, but similar. It'll get larger. Great job, Julia. And so since it's getting larger, if we went from 95 to 90, the interval would get wider. If you go from a 95% confident to a 90%, so you're being less confident, your interval would get wider, which means it would contain less values. Your interval would get what? Because it's going to be less confident, less values. Your interval is going to be wider. So if you go from a 95 to a 90. So if you go reverse, instead of 68, 95, 99.7, you go 95, 90. The percent, yep, smaller. Exactly. Great job, Julia. Does that make more sense right here? How to find the margin of error, how to find, the idea of like percent confidence, how wide the interval is. This would be a more precise interval, but less confident. So this also goes over the idea that when an interval is more confident, it is less precise. When an interval is more precise, you can lower the confidence to get more precise. Like the interval is going to be smaller, which is good. We can give a smaller range of values, but we're less confident that the truth is contained in that interval. So hopefully that helps out right there. You're welcome, Julia. Thank you so much. Paige, we'll do yours right after one more of my Pearson. Let's do one more of my Pearson here. The rat maze problem. We're going to do the rat maze problem. Then we'll hop over and do Pages about how to create a variable. Let's do a cut in the video. These help me out later on finding the spots. The rat maze problem. Ooh. I think yesterday the coffee hadn't kicked in. I did the rat maze problem. Oh, isn't there the T one? Oh, man. The T one we can do quickly. I want to do the one next. Here we go, the rat maze problem. Let's do this. My background's been working. That's awesome. Here we are with the rat maze problem. Find a 95% confidence interval for how long it took them to find the food going through this rat maze. Let's go ahead and take the data right here, and you notice there is a column name. I want to point that out here that there is a column name. So since there is a column name, when we go to copy it, we're going to copy to clipboard, and we're going to hit copy, Control or Command C on the keyboard. And now let's go ahead and go over here to jump. Doesn't matter where you're in jump. As long as you're in jump, you can go to File, and then New, and then Data Table. File, New, Data Table right there. In the new data table, since we have a column name, we have to go to Edit and then Paste with column name. That is so key right here that we're going to paste with column name. Make sure you do that, and you will see that it is blue, meaning it is quantitative, and you have a column name. If you got this, if this is what you see, start over. Just delete it. Start over, redo it, and paste with column names. Make sure you paste with column names. Don't try to fix it. Just start over. So now that we have the data right here, we have to start by making a 95% confidence interval using this data. Let's go ahead and full screen it. Here we go. And we'll go to Analyze and go to Distribution. And then we're just going to double click it. Let me slow that down a little bit. Analyze Distribution. Someone's like, whoa, 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 whoa. I always forget to stop a little bit. Analyze Distribution right here. Let's go ahead and click OK. Now we're going to double click this. When you double click it, it'll put it into the Y columns, which means we're going to analyze it. And we click OK. Next, we're just going to go here. We're going to make it look all nice and pretty. And we're going to go here to the top right arrow. And we're going to click Stack. That's going to put it in horizontal layout. Then we're going to click the second red button. It gives us all the options. And we're going to go here to Count Access just because it's good standard policy to do that. There we go. Nice looking histogram. And we have everything. But we're going to do one additional thing, which is going to be so important for this problem. We're going to go to Redo, Automatic Recalc. Now, this is a big help for this problem as we work through this. If you don't do this step, you have to do additional work. So that's going to save us a lot of time later on. Make sure this is checked. If you want to know that it's checked, you can check back here under Redo, and you can see Automatic Recalc is checked. Don't uncheck it. It just needs to be checked right there for the tricks I'm going to do in this problem. So now that we have our data right here, let's go ahead and take a look at the problem. Where's that problem at? Okay, it wants a 95% confidence interval. Cool. JMP does that for us. Down here, ooh, too much output. Right here, JMP does the 95% confidence interval. We have from 46.11, so 2 decimals, 46.11 to 58.97. 46.11 to 58.97. And it wants the shape of the distribution. Which shape was it? I need to close some JMP output. We'll do that after this problem. So this goes from 20 to 100 by units of 5. Okay. Let me just explain what I did. I double clicked this bar right here. So I double click it and I get to this menu, 20 to 100 by units of 5. And now it looks like this. We compare. Nope. Nope. I need to vanish. It is. It's always the last one. Why is it? It's always like the last one, so I have to vanish and look at it. Yeah, that one has not... It's close, but not close enough. This is the correct one over here. That is the correct graphic, so we choose this one. Next, choose the normal quantile plot. Normal quantiles plots show you if something is normal or not. They can only go up and to the right. 320's done a lot of these. This one right here is a perfect normal. Literally, we're only choosing between this one and this one. By the way, normal quantile plots work. They can only go up and to the right. This one is just madness. I've never seen anything. It's not possible. So they follow this pattern where the points have to go up and to the right. This one goes down and to the right. Can't happen. Now, why is this the perfect normal? If we look at a normal quantile plot, the way normal quantile plots look is a normal quantile plot found right here under normal quantile plot lets us see if something is normal. It's one way to check the normality. It's for your test. And you go right here and you see this red line. This red line is the perfect normal, and we're going to kind of squeeze this a little bit here to make it look more like the graphics down below. And you see this one right here that I'm over follows a perfect normal. So this one is perfectly following the line, which ours does not. And this one, there's that point. There's that point up there. It is going to be this one. Man, I hate how they have that looking. There's this, so the JMP does a little bit differently. And so I always hate, like, you can kind of tell because it's a perfect normal, follows the line perfectly. This does not follow the line perfectly. There's some deviations, especially this point, which might be hard to see. There's a point right there, which is far away, and that's that point right there. So it is definitely, didn't reselect anything, did we? I have misclicked before by clicking up there. So now we need to talk about the data right here. This data has a problem. The problem is this. It's got an extreme outlier, and this is a smaller data set, which is probably going to cause issues with the distribution of the mean. And there is the data point right there for a data set of something like 40-ish values. We can take a look. How many values did it have? It had 20 values, 21 values. Okay, so way less than 40, way less than 40. So this right here is not good to have this extreme outlier. Mine is 90% confidence. Great question. If it wants 90% confidence, go here to the arrow and go to 90% confidence right here. Does this make sense, Emily? Great question. Thank you for asking. Go to confidence, 90% confidence, and jump. Yep. Do you see the red arrow right here? Go to 90% confidence right here, and that will give you the 90% confidence interval right there. Does that all make sense how this is now the 90% confidence? So go to the red arrow, go to confidence interval. You're welcome. Thank you for asking. That's what we're here to do. I'm here to answer questions, here to help out. And so we have the right plot. Now we go right here and we look at the randomization condition is met. The normal probability plot is, yeah, here it is. Where's the outlier? Here's the with one outlier. Without the outlier, the conditions seem to be met. The histogram is roughly unimolar and symmetric with no outliers. Yeah, this is talking about with the conditions met right here. So this one looks to be right. The randomization condition is met. The normal probability plot is relatively straight, which is what we want to see, relatively straight, with one outlier, which we see all the way up there. Without the outlier, the conditions seem to be met. The histogram is roughly unimolar and symmetric with no outliers. Yeah, it's without the extreme point. Without that point right there, roughly unimodal and symmetric. Roughly. And that's something to use for your project. Roughly unimodal and symmetric. Hints for the project. Anyone working on the project, maybe that wording right there of it's roughly unimodal and symmetric, maybe a little flat on the top, but roughly unimodal and symmetric. Now this is important. I want to highlight this again, that we went and we turned on the auto recalc. You need to have auto recalc on right now with what I'm about to do. I'm going to highlight this point. Notice how it's highlighted. You could also just click right here. So with that point clicked, we're going to go up here to the very top of the menu for either the Mac or the PC, and we're going to go to rows. Can you do the Hoping to Lure Shoppers? Yeah, we're going to do a 321 after this, and then we got another My Pearson. That is third on the line. You got it. We're going to go here to hide and exclude. So make sure you watch your numbers, because if you have automatic recalc on, watch what happens to my numbers when I click hide and exclude with that point clicked. Did you just see them all change? If all your numbers change down here, you've done it correctly. So your numbers should change. You need to make sure, though, that you have on automatic recalc. And I don't think you need to turn it on now. So if you're following the instructions, you should have it. And I am building a 95% confidence, 45.41. 45.41. And where's my jump output? Oh my gosh, I got so much jump output. And 55.62. Let me look at the decimals on that. I don't want to get a decimal place wrong. That is correct. Does the maze meet the requirements of lasting at least 1 minute? Nope. It does not either way. We think the true mean time is below 1 minute. So the maze does not meet. Both confidence intervals are entirely below. That looks to be right. Woo! Sometimes I want to double check. Like if I was a student, I'd be double checking these. Let's take a look at the question Paige had about how to create a new variable. So let's go ahead. Let's do a break right now. Let me close out of jump. We might break the world here. I don't know what that looked like on stream. Okay, jump has been closed. Jump is reopening now. Jump 15. We can use jump. I might download jump 16 later on. Jump 16. What? Hey, Brian, if I have a sample size 15, you got it. Yeah, Jonathan, you got it. For the one sample T, excellent work, Jonathan. Thank you so much. Great question. Sample size of 15, degrees of freedom 14. Yep, for one sample T. For one sample T. Yep, two sample T will be a different world of answers. To do variable creation, let's talk about that right here. Variable creation page. Let's do it. Could you remember how far to the golfers at the country club? Yeah, Julia, you got it. We've got 3 questions before that, but we will be doing that one here soon. Let's go talk about some features. You're welcome, Jonathan. Thank you for swinging by. Thank you everyone who asked all the questions. We love it. Let's go over here and look at some variable creation. We have this up from earlier, so let's kind of review the code right here. So we've got the code up, and we're talking about variable creation. So when it comes to variable creation, this is not the data frame you're using right here. So this goes out to Paige and everyone who's doing variable creation. We have here a linear model being made. That's what LM stands for. We're predicting the variable height. So this is predicted height is being explained by GPA using the data frame survey 10. So just understanding the code, and then we're saving it into the object model. Anytime, Paige, you bet. And then we're doing a summary of the simple linear model. Yep. Feel free to ask questions, and thank you for hanging out. I'll always try to get to it. I understand if people have to leave. Like, you could be like, I have a class, I have to run, Brian. Sorry. Like, I'll put it in the video for you. You bet, Sydney. You got it. We got so many questions. Let's keep doing them. And so here is where the variable creation is happening, Paige. This is where the variable creation is happening on this line. So I'm taking two variables and whatting them. I'm taking two variables. So if you look right here, I've got two vectors. This is a vector of students' weights. That's just a vector, just a bunch of, I asked everybody what's their weight. And then I asked people, how much do you want to weigh? And that's all the weights people want to weigh. No one put decimals. It's so funny. When it came to weights, people were very precise. A few people must have put decimals because it's doing it down to a decimal. We're dividing them. Yep. And so when we do this, we get the ratio right here of somebody's weight to their desired weight, which I think is kind of interesting because if it comes out to be 1, and you don't have to worry about analyzing this too much, but if it's 1, that means somebody's weight is equal to their desired weight, like it's a 1-to-1 ratio. Where if somebody has a positive number, that means somebody is more than their desired weight. If it has a number below 1, if the number is greater than 1, they're more than their desired weight. If the number is less than 1, they're less than their desired weight. And like you can tell, like this person is 30% more than they desire to weigh. A whole bunch of different numbers right here. Kind of an interesting variable, I think, to create like where are you at to your desired weight? What's interesting is there's so many people at 1. I might do an additional analysis here, right? Which is pretty crazy to me. A bunch of people are like, I weigh 190 and I want to weigh 190. Hey, no, and know what? More power to you right there. I just didn't expect to see as many of these. I'm shocked by that. So I stored this into a new vector. Does that make sense? And then what did I do right here? What is this line of code doing right here? It's taking the vector and putting it where? And so you can't quite do this example, and I'm going to call it that now, sure. This is taking that vector and doing what with it? So this is dividing two vectors, storing it into this vector here, and then I'm taking this right here and putting it where? I'm adding it to where? So this is taking the new vector I've created and putting it where now? Because it's got the data frame, $sign, so it's going to be where now? That new vector, and you're going to see it twice by accident now. The new vector I've created is where now? So by using this line of code right here, where I take a vector, and then I go to a data frame, because I could just call this like, I wouldn't do this, but it doesn't make sense to call it that. Do you see what happened when I ran that code right here? It's taking the vector I've created, and you could just, like if you wanted, you could just skip this step. We'll call it Darren. If you look right here, is this making sense what's happening right here? We're dividing two vectors, and then we're creating a new variable right here in the data frame. Does this all make sense right here, Paige? Like how these two vectors are getting divided to create just this sort of, I have to highlight the whole thing. And I'm hitting Control Command Enter to just run like the code as is. And so this is what this vector is, and then it's being stored onto this data frame right here, and you can look inside the data frame. Yep. So it's being added onto this data frame. Just think of this like an Excel spreadsheet, and at the end of the Excel spreadsheet right now are all the things. And I've been storing it multiple times. So the code I've been running has just been storing this vector onto the data frame. So when you go right here, you can just see it's been added onto the data frame. So now we're going to add the variable. I'm going to use one of the ones I've created that doesn't have the crazy names. We're going to add it to the new model, our original model. And so we had a model here. Here's our starter model. Awesome. Thank you. Yeah. Thank you, Julia. Yeah. Thank you, Julia, right there. Let's throw 50 points. Yeah, we could come back and do it here at the end again. Sometimes we're like, when did we last do that one? I could just say, I did these all last. I'm just kidding. I can't remember sometimes. And so we go right here. We take a look at it. Julia, you're awesome. And we can circle back and do it again and talk about it. With this right here, what does this indicate to us, Paige? What does this indicate to us right here? Like we got a low p-value right here. That means the variable Brian created does what? So we're trying to predict somebody's height. And GPA, interestingly enough, GPA brings new information about predicting somebody's height. If you ask someone their GPA, it actually gives you information about their height. So what does knowing how close someone is to their ideal weight also do about their height? That's so interesting. It's actually a really good variable. brings new information. That's exactly it. That's what low p-values mean, is that the variable in the multiple world brings with it new information not accounted for by the other variables in the model. And that's because the p-value is below 0.05, which as Stat201 knows, and they've been reviewing, is that we reject the null. And the null would be that this variable is not significant in the model. So think about this. That means we have evidence that this variable is significant. There's new information, there's not completely redundant information. Sorry, everyone. There's not completely redundant information in this model, or with this variable. There's new information supplied by both variables in the model. We don't really care about the intercept. The intercept it's a value when all x's are equal to 0. It's like, we have evidence that the intercept is not equal to 0. Cool. It's a value. But yeah, that's excellent work there, Paige. Is it making more sense? Do you feel like you have this one figured out? You've coded it for yourself? And we'll do another one right here. I think we had it was like a T1. Ansley asked, using the T-table software, estimate the values. That's one of my favorite ones. This is like a treat for Brian right here. We're going to do Brian's favorite problem. Perfect. Just forgot the code for Kane. Yeah, no, Paige, don't worry. Just glad you swung by, Paige. Glad you asked. Whenever you're stuck, just let us know. Email, Discord, YouTube videos, and then check out the questions people ask, because I always timestamp these. Let's do a cut in the video. Awesome. And I'm ordering some new Ethernet cables. We'll get the internet working eventually. Come on, Sudden. Like, we need to reach out. I seriously need to just buy the Elon Musk internet. Need to go buy it. Hopefully it's good. Watch us have no problems then. Just chip in your brain. Okay, let's go get that using the T-table problem. My favorite problem. This is Brian's treat right here. For Brian, we're going to do using the T-tables. Yes. Here we go. Brian's favorite problem. Let's do this. Ooh, we got a hard version of the problem. Let's go pure Hackerman on this. You ready, everyone? We're going Hackerman on this. Here we go. We're going to get all of our brain power right here. Make this happen. We're not using any sort of software. We're just using our brain. The first one's super difficult, though. But we can do it. I'm not scared. Watch this. You ready? I can get this second one. You ready to see a 50? Let me think about this. That first one's really difficult. First one's so difficult. This second one... Dang it. It's the first one. Darn you, first problem. That first one's so tough. I knew it. The second one's so easy. 2 more tries. That's not the answer. I'm thinking really hard. Let's get the actual answer. You ready? Mewbot. Give us that T-applet, Mewbot. Help us out here, Mewbot. T-applet. T-applet away. Was it 12 degrees of freedom? 13. How close were we? No. Really? Wow, my brain was wrong today. 1.7. Oh, yeah. That's how it works. Wow, we got that off. I got to practice my T-distribution memorization. Oh, yeah, let's talk about what we did right here, and let's solve it the actual way, and then take one more guesses here. Okay. A little bit of fun right there. We can't do the repeat of the problem. Okay. So when you do these problems right here, you have to use the T-applet, or you could try to memorize it like I did. The way these problems work is the T is just like the Z. So I know all the Z-scores in my head for these. I know the Z-score for 95% is 1.96. So the T is always going to be a little bit wider than the Z, which actually relates to one of the last problems right here, which you can see the answers for. Yeah, there's answers. The T distribution is always going to be a little bit wider. It's going to have fatter tails. It's going to be pressed down a little bit. And we can see that visually right here if we give it less degrees of freedom, and also the T is further out than the Z. With a lot of freedom, the T will eventually become the Z, and I know 1.645. I also know numbers like 1.96, classic 95%. I know 2.3263, and I swear it's 2.3263. I know you're saying it doesn't round to that, but I promise you. And I know 2.5758. So those numbers right there are numbers I've memorized, and with this, we can actually use them to find the T-score. but we don't have to worry about it. Which one was that? Oh, wait, let's turn off the completed problem. And let's go back to it just briefly here. Oh, we get one last point of redemption right here. 90% confidence. Okay, so I think it's the same one. Well, I bet it's 1.78. So when you do this, you need to go to the t-applet right here. You need to go to 90% confidence, and it's in the chat right there. With 90% confidence and with 13 degrees of freedom, you can see the t-score down here of 1.78. This is a confidence interval, 90% confidence. If you have time, could you quickly over section part C of the project? Yeah, Sydney, I think we got time. We'll go take a look at that in a second here. And so this is a 95. Now, real quick question. What was the sample size for this one sample T? This could be a test question. Pretty easy one if you get it, as long as you know how to do it. What was the sample size for this one sample T with 49 degrees of freedom? So let's go over here, put in 49 degrees of freedom. And if it's a one sample T, 95% confidence, 2.01. I guess something close enough to that last time. And the sample size would have been what? If this is a one sample T, the sample size would be 50. 50 because the degrees of freedom are n-1 right here. So we should get everything right. And that's actually how we want to solve it. This one right here is very similar. It's doing a 99. Ooh, that one is very hard to guess. This one right here, unless it doesn't want. This one I'm not going to have a good guess for. 5 degrees of freedom, 99% confidence. Because with 5 degrees of freedom, the curve is so drastically different from the normal curve. And at 99% of confidence, 4.03. I would not have guessed that. 4.03. And let's take a look right here. 4.03. The 95% right here should be right. I'd be shocked if it's not, because that's basically the z-score. So I really like that bottom one, because it's going to be so close to the z-score. Yes, good. It probably would have accepted 1.96 with the margin of error. Oh, it didn't. Wow, I was right to guess 1.97. Does it really want decimal place accuracy? So it looks, I'm shocked it didn't accept the other one. If you want to actually get the answer, go here, enter in the degrees of freedom, and do that. Oh, it's 1.98. So 1.97 was close enough to their margin of error. Chapter 14, hoping to lure shoppers. Yeah, we got that one. Here, let's do that one next right here. I think we haven't done that one today. But does this make sense? How to find t-scores with the percent confidence? Who's following along right here with the t-scores? So we take the degrees of freedom, put that into the t-calculator. It then draws the t-curve for us. And when we draw the t-curve, we then put in the percent. You're welcome, Sydney, Savannah, anytime. So it then draws the curve for us. But how many t-curves are there? There's infinite t-curves, and the t is like the z, but the t has with it degrees of freedom, telling us which t we are using. Let's do that, hoping to lure shoppers downtown. I think people mentioned that earlier. Savannah, you might have mentioned it. Sorry, I'm trying to remember. There's the ones we've done today. So good to see you here, John. Hoping to lure shoppers downtown as city builds a new public parking garage. Let's go ahead and copy the information from this problem. I need your help right here. So your help is needed to identify the parts of this problem we have. So can you identify the notation in this problem? But chapter 14, I watched the OH video explaining how to do the psychology experiments. We just did that one earlier too. Lizzie, let us know if you have questions. We did the psychology experiment with the rats earlier, I believe. What do we have notation-wise right here? And we're missing something right here on this. We don't have something yet. What do we have notation-wise? We've got 4 things. Who can identify any of the 4 things in here? So go ahead. I still understand. Can we go over it? We might not have time. We'll check out. That'll be one of the later ones. We did it about 30 or so minutes ago. Yeah, it was about 20 minutes ago, Lizzie. Check out there. If you still have questions, let me know. I think we did it yesterday and we did it today again. So we haven't done this one yet today, so that's why I'm doing it. Does that make sense? Y bar equals 128. Great job. That's the sample mean. We can try to loop back to it here in a little bit. I'm just going to keep trying to do as many new things. Don't worry, though. N is equal to 44. That's the sample size. And then this is the standard deviation. And then the degrees of freedom, which are right down here. These are the degrees of freedom. Equals to n minus 1, because it's a one sample t. and 43 right there. So that has everything, but we also need to know the percent confidence. This star right here means it's relative to a percent confidence, and we should find that out later on in this problem, a confidence interval. And so with this one right here, we did get this one wrong yesterday. We're not going to get it wrong today because we're not going to get tricked. The sample size should not be at least 10% of the population. The sample size should be less than 10%. That's where I made an error yesterday. The data are randomly sampled of all days. We would assume that. The data is unimodal symmetric with no outliers. And we do not want the data to be dependent. We do not want the data to be dependent. Create a 99% confidence interval. So where do we need to go? To create a 99% confidence interval, we need to go to the t-applet. So we're going to go to the t-applet to get the last bit of the equation we need, which is appearing in the chat right now. And I think it was, how many days was it? 44 days. And so the degrees of freedom are 43, and we want 99% confidence. That means the t-statistic is 2.695. 2.695. If you didn't see it, it was right there, 2.695. And let's go and plug that in to the formula right here. 2.695. And the y bar, 128. The S of 12. There we go. There is the information we need to solve this. And what I usually do right here is I solve for the margin of error first. This is going to be the margin of error. Let's just highlight it with the margin of error. This is the margin of error. Let's solve that first. And here we go. 44 square root, 12 divided by that, times by 2.695. As long as we didn't create a mathematical error, we have now found the margin of error. And let's just put the calculator right over this. There is the margin of error, 128 plus or minus this. And let's go back. So we need to go copy this and go to 128 plus this. And that's 132.88. And then we take 128 minus this right here. And that's 123.12. There we go. And let's see here, explain what this means. There is a 99% confidence that the mean daily income will, that's the fall word I don't like. I think there's 99% confidence that the interval contains the mean daily income. Yes, I don't like the words falls. We don't try to use that in statistics because the interval will contain it. It's not that the mean falls in the interval. Explain what 99% confidence means. It means 99% of random samples of size this will have a mean that is contained in the interval. Last but not least, there's a lot of confidence interval interpretation right here. Since the 99% confidence interval, does it contain? Let's see right here. The consultant who advertised for them said he would expect 124, or they would expect 124, and our interval does contain 124. So since the 99% confidence interval does contain, it contains it, the prediction of the consultant is plausible. We would believe it. We think it's a plausible. Oh my gosh, I knew it. I knew my streak of everything getting right. Did I forget? Wait. The data are random sample, unimodal, no outliers. That should be correct. Do we get an error there? Double check everything. That's right there. Where am I going crazy? Oh, it's this one. Oh my gosh. What did I select? I didn't even look to see, but that's 100. 99% of sample sizes of 44 have a mean daily. Will produce confidence intervals. My eyes just quickly read it. Sorry. That's our one mistake today. We're allowed one mistake each day. That's our one. We've done like 6 or 7 problems. One mistake. It's the one mistake. No more mistakes, though. That's it. So 99% of samples will produce confidence intervals. And that's exactly it right there. So yes, I think I was saying that as, and then I was just like, yeah. I think my eyes looked towards the structure of it, and that is the 100, right? Yep. Thought I made maybe a decimal error. Streak is over. No. Sad times. What question, if you have time, could you go over section 3, part C of the project? Let's put a cut in the video here. Let's talk about that. We got this. No more wrong questions. Let's do this. Section 3, part C. Here we go. Let's talk about this part of the project. Let's do it. Okay. Use JUMP to calculate a 99% confidence interval for the proportion of days with high casual demand. Include the screenshot for the JUMP output. Okay, let's take a look. So in Jump, whenever we have categorical data, and the golfer one, you bet, Julia, let's do that one next. We haven't done the golfer one yet, so that's a great one to do. When we do confidence intervals, we need to go to Analyze Distribution. And with Analyze Distribution, we're going to select a categorical variable. And maybe we want to know the proportion of students who were born in Tennessee. So we're just double clicking this right here. And then we click OK. And we're going to click the top red arrow. Let's go to the zoom. Under the top red arrow, we're going to go to Stack. We have a lot of options here where we can go to histogram options. We can go to account access, which we should have. We can go to histogram options, and we can go to show counts. So excellent stuff right here. This is kind of like your project right now, but not exactly like your project. This is categorical data. So we have here the counts of individuals who are not born in Tennessee and the counts of individuals who are born in Tennessee. If you have data selected, you can always hold Control or Command to click and deselect it right here. So when we're doing this, we now want to create confidence intervals for this. To create confidence intervals, let's go here and let's go to the second red arrow and go to confidence intervals, and then we can select whatever we want. If it gives you something interesting, you can go to other, and with other, you can enter in whatever value of confidence you want, and you can notice it's doing 1 minus alpha, which we talked about today in class. So here we are. We'll get the 91% confidence interval, 91% confidence interval. There we go. And you can see right here, I am 91% confident the true proportion of Stat 201 students born in Tennessee is contained in the interval 58.13% to 61.93%. And make sure to use your interpretation right here. I am blank percent confident that the true blank, make sure to know if it's proportion or mean, is contained in the interval blank to blank. I am 91% confident that the true proportion of students born in Tennessee is contained in the interval 58.13% to 61.93%. Does that make more sense right there? I think, was it... Trying to see who asked the question about the project. I hope that makes sense. I think that's got it right there. Let's head back to space, do the golfer problem. We got no more mistakes left today. We got to ace the golfer problem. Got to go hole in one. Let's see right here. You're welcome so much. Anytime. This one is all correct. Thank you, everyone, for asking all the questions. How much can we do of the assignment during office hours today? Suppose, it's too easy. I like that one, though. How far do golfers at a certain country club drive the ball? A histogram is shown right over here. So we've got the histogram, and let's take a look at this. We're trying to calculate the mean driving distance and create a 95% confidence interval. So let's go grab the information. And what do we have right here? I do kind of like the way they display this because they don't put it in notation, and sometimes they do. They kind of mix up how the problems are presented to you, so you have to know how to handle different bits of information, which is kind of the point of this class, because we don't know in the future how someone will present a problem to you. We just want you to know the tools and techniques to use. So can anyone identify the notation for this? So we have 4 different things right here. So here's the formula. So what is the notation for this problem? What notation do we have? And I guess technically, so yeah, I was going to put that in the spot, but so what do we have notation-wise for this problem? Oh my gosh. 201. What notation do we have for this problem? So identifying the notation is always key for these. What notation do we have? And so I've put the equation right here. Once we know which equation, that should help us out a lot. So having the equation will be a big help for solving the problem. So we have the equation, and now we just have to figure out what goes where with the notation. Any of the notation, what do we have? Great job, great job. That is the sample size. Thank you so much, Julia, right there. These are the degrees of freedom. And this is the confidence level. So that's the confidence level of the interval, which is relative to the star. And this is the standard deviation. And this is the sample mean. There we go. That is all the notation right there. So we can start plugging in the numbers. Thank you so much for the help right there. And let's start plugging in the numbers. Let's go to a different pen color. One of these days, Microsoft Word will stop changing my pen colors. Not today, though. 287 point... It's hard to see, right? Let's go back to it. Oh, it was green. Ha ha. There's a way I figured out to make it stop changing. You have to double select the color because it uses like the last color I've been using. So I have to like change it twice. And I think that works. Because then it's like, oh, you're using a green pen, but you last used a green pen. We'll worry about that T statistic in a moment. Mubot, help us out here. Show us where that T-applet is at. If you're wondering where the T-applet is at, Mubot's going to put it in the chat right here. He was just putting in the chat a moment ago. And here's the T-applet. There are 201 degrees of freedom. We're building a 95% confidence interval. And so let's go here. And the T statistic is 1.972. And Mubot just put the T-applet in the chat. So that's the T statistic right here relative to a 95%, 99% confident. So that's going to be about 2.62, about 2.62? 2.6. 2.60. 2.601. 2.601. Here we are right here. There we are with the percent or the T-score relative to a 99% confidence interval. And let's take and go over here and do 202 square root 9.1 divided by that and multiply by 2.601. And there we go. There is the margin of error, 1.665. And yeah, that's the portion right here, 1.665. And now we're going to take and just add and subtract that to the mean right here. So we're going to take this right here, 2.87.8 plus the margin of error. So 1 decimal, 289.5. And then we take right here 287.8 minus, and we get 286.1. Interpret this interval. What is the problem with the experiment? Ooh, got some interesting questions right here. Let's see right here. A histogram of the driving distance of the leading golfers. Uh-oh. I think so right here. It's not really that skewed. The data is not that skewed. That's not the bigger problem. The 10% condition is not satisfied because the sample is too large. No, it's... No. The problem is they're taking the leading golfers. The data are the mean distance for each golfers. Is that a concern for the interval? Yes. The mean driving distances have less variability on which they are based. This can result in an inaccurate interval. Yeah, they're taking it on the mean. They're not taking single observations to figure out their goal. This is such an interesting question. Their goal is to figure out how far do the country club golfers drive the ball on average. And they're talking to only the best golfers at the country club, and they're taking the mean for those golfers. So there's less variability, and they're taking the top golfers. So this is kind of one of those questions that has problems. As long as we do all the work correctly here. Gosh, my gosh. Did we do the... That's all correct. Brad's brain is shutting down today. What did we do wrong on... Where did I get 99 from? Where did I get 99 from? How did I switch to 99% confidence? Sorry, that's where Brian has worked too many problems today. (95% confidence). 95% confidence. Mark your notation. So 202 square root 9.1 divide by, and there's that, 1.972. There's that. And go right here. You know what I'm going to do? 287. I'm going to go over here. 287.8 plus this. 287.8 minus this. There we go. You know what I'm going to do? Is it 1 decimal? It's called How Not to Make Mistakes. There we go, that. There's the, that looks accurate. And here is this one. And was it 1 decimal? Round to 1 decimal. I did so quickly, I got a little bit worried there. But that right there, and I do like solving things a lot better in R, but we don't use R in this class, so I don't expect people to use R, but it's just so much easier. So much easier. You can see the number. You can be like, that number looks correct. There's that standard deviation I found. And in truth, what I'd like to do for this problem is I'd prefer to just take the standard deviation 9.1 divided by the, so this right here was 9.1 divided by the square root of 202. And so this would solve right here. What's really great, yeah, and then, oh, and then we need to times it by the t. So, so we need to go qt, and let's times it by that. And that should, let's put this in parentheses right here. Yep, that did work. This is me getting revenge on the problem if anyone's wondering. Like, I'm going to make it so we can just instantaneously solve this problem. Because I'm just like, I'd just rather build a solver for it. And so that's the lower, and that's, you know, it's in the reverse. So let's go ABS of the margin of error. And go right here. And that should give us the upper now. Or because it's the minus, that's fine. And now we have the lower and the upper. And then let's go back to here. Now that we've built the equation, the numbers change. So we're going to build a solver for this. Or we can just go right here. So 285.8. 285.8. There's that number. And 8.1 standard deviation. And then what's the sample size for this problem now? Sample size is 202 still. And then what's the percent confidence on the interval? Percent confidence is 95%. And that's correct for 95%. And so we should get the answers as follows, which we can see 284.7 and 286.9. So now that we have a solver right here, it can just instantaneously be solved since we've written the equation. We'll go one step further. I don't know if there's more questions, but ask them. But this is my revenge on this question. Let's go here and build a solver for it. Like, we're going to take this and just make it so we can, we don't even have to worry about it. So we need to put in the mean. The mean is equal to this. And this will be mean now. The standard deviation is equal to that. So that's 8.1. And we need sample size. Sample size is equal to this. The degrees of freedom are equal to sample size minus 1. This is my revenge. Brian gets revenge by coding. The confidence level is a bit odd, though. Will you over the... Yeah, let's do that one next here. The flight, you bet. Let's do that one next, at least. I've almost got this coded so that I can, like, do this right here. I was like, man, I hate getting problems wrong. It just grates against me. The conf level is going to be... Someone needs to enter in percent confidence. Percent confidence, if someone enters in like 0.95, then the conf level is going to be, or conf value will be 1 minus percent confidence divided by 2. And now that we've done this, we've built something here where we just enter in the values and it'll give us it. So if I ever come back to this problem again, and I can make this even better, that just asks you, like, what is the mean? What is all this? But we're going to head over to your problem here because we're just building something right here down below where you just, it literally solves it for you. It'll ask you, like, what's the mean for the data? What's the standard deviation? Like, I'll just show that one right here. I need to change this now to where I go to as numeric. Let's go here, read line. And we say, what is the mean? And then we just store this as mean, and then somebody, not mean, and then it says, oh wait, what is O? and then it says, what is the mean? And you just enter in your value. And then it'll store that as the mean. So now we can enter in like this, and we could just run a function. I'll come back to that later. So will you go the one, the similar looking question on the homework? What about the flight destination? Yeah, I think so. Let's do it. We've done a lot of these today. Will you get to your flight test? I think is it this one right here? I'm showing the whole thing. It's the homework one. Let's do the homework version of it. It is that one, and it's on the homework. And let me go get the homework version. I need to log back into my Pearson. Let's go to space. Right here. And assignment manager. Here we go. I'm almost there, Elise. Come on. And now it's announcement manager. Whoops. Assignment manager, chapter 14, homework. Replace questions. Here we go. We've done a lot these days. We've done a good job today. Here we are. Will you get to your flight destination on time? Here we go. Here we go. Thank you so much, Elise. And thank you for waiting while I was just having a little bit of fun coding right there. People might think I'm crazy, but I really enjoy coding. I really enjoy it. What's interesting is we can use the code to solve this question too. So I'm actually going to use this to check the question. So you'll see in a half second here, I'm going to use it as a checker. We have all the conditions met. Yes, all the conditions are met for this right here. So we have that these are randomly sampled flights. They're less than 10% of all flights, and the distribution meets the nearly normal condition, probably by large enough n, because the sample size is large enough that the distribution of the mean will be nearly normal. The next question is going to ask us about the confidence interval. We want a 99% confidence interval. To build this confidence interval, we need to know the degrees of freedom here, which are going to be 71. n minus 1 are the degrees of freedom. So with these degrees of freedom being 71, we go here, put in 71, and we get the t-statistic for a 99% confidence interval. So the 99% confidence interval has a t-statistic of 2.647 for a 71 degrees of freedom t. And make sure the t output on the screen is the one you're going to right there. So let's go ahead and take this problem as written, and then we'll use the solver. And let's go over here. And let's go and plug in the numbers. So we have here y bar plus or minus t star with n minus 1 degrees of freedom, s over square root of n. And we see right here, we have most of the notation written out for us. The degrees of freedom were 71, and the t statistic was, I forgot already, 2.647. And make sure to go to the t-applet and get the t-statistic. And get the right one. Don't get the wrong one. We already did that once today. So we go here and put in the y bar of 2.40833 plus or minus 2.647. And then we go right here and put the s of 2.60320 square root 72. So that's got all the numbers written. We're going to solve out for the standard error and the margin of error first. So there's the standard error in the last part times the t-statistic, which gives us the margin of error. And let's go ahead and take 72 square root, copy, 2.60320 divided by that. And there we go, times by 2.647, and that is the margin of error. So the margin of error is 0.812. And let's go right here, and let's take the mean of 24, we'll copy this, 24.0833 plus this, that's 24.90. Double check. Yep, everything rounds up, rounds to 2 digits. And then we take the mean minus the margin of error. This is the margin of error I'm entering in, 23.27. And we probably got it right, but my solver over here can also solve it. I made a solver a moment ago. It's got the standard deviation right here. So let's go ahead and it's going to ask me what the mean is. We'll just write the mean. It's easier for me to just input them at the moment. So the mean is 24.0833. The standard deviation, and it wants to 2 decimals, good. The standard deviation is going to be 2.60320. The sample size is 72. The degrees of freedom is going to be found for us. The percent confidence is 99% confidence, and I believe I have it rounding to 1 decimal. There we go, and that should do it. And unless I did, yep. So 23.67. And there, oh, we got something different. Now I'm worried. 99% confidence. Oh my gosh, the sample size. 23.27. There it is right there, and 24.90. Exactly the same answers. And that's good news. So we used my checker to solve it. And yep, if I had been wrong answers, my head would have just went, you just seen me. I'd have been like, what the heck? Like, what is going on? Just insanity. Interpret the interval for the trainer planning to fly. We are 95, or when we can be 90% confident, 99% confident the interval contains the true mean monthly percentage. I am 99% confident that the interval contains the true mean monthly percentage between blank and blank. I get scared. Can't lose your confidence. Can't lose your cool. You gotta show these intervals what's happening. Does that make sense right there, Elise? And what I was going to finish up with this right here is this solver I was building. So that's the round right there. It's called rounding. Rounding is currently set to 2. So there's the rounding. And so what we want to do is we had that read line earlier. Here's the read line. Awesome. You're welcome, Elise. This is something for like 474 right here. Oh my gosh. Whoa. Okay, there we go. So degrees of freedom. Yeah, so we need to go here. Oh, we don't need to calculate degrees of freedom. That'll calculate for us. And then we need percent confidence. Oh. There is percent confidence. Okay, I think that's got everything. And then sure. And then let's go here. Fun. Here we go. Last little bit. I should have deleted that. Last little bit. This is my revenge on my Pearson. Calculate interval. That's got it. Okay. And new. Okay, calculate t-interval. Let's check this out. You ready? Let's give this a whirl. So calculate t-interval. Oh, that's not a calculate t-interval one. I think we can do it for this one. Calculate the 95% confidence interval right here. So we got our calculate t-interval up on the screen. Let's raise the bar right here a little bit. And let's check out our calculate t-interval function we wrote right here. So this is my function I wrote right here to help out with these problems. So I can just solve them instantaneously. Like, if I'm going to do all this by hand, why not just use this right here? So it first asks me, what is the mean of the data? The mean of the data is 324. What is the standard deviation? The standard deviation is 35. What is the sample size? There's 40 hot dogs right there. What is the percent confidence? 0.95. Oh, it got mad. Oh, that's fine. There we go. Oh, and it, the round. I should have put in the thing for rounding. Should ask you, how do you want to round your answers? So that's a bummer. I didn't put that one last command in there to round it. And that's going to round to 2. I could change that. And that's got it. Solved instantaneously. That's what I like. Have you gone over the suppose we make 95% confidence population mean for sample size 15? Yeah, I'll do it next right here. You got it, Clarissa. And this is why I like using coding right here, because coding can make life super easy with what I created right here. I can just add the one last thing in, like your rounding. If we asked right here, how do you want things rounded? So we go right here and we say rounding. How many decimals? And so now my function will ask me at the end how many decimals at the end. It'll say how many decimals do you want? So just looking at this one again right here, if we were to redo it with the function we created right here, what is the mean of the data? 324. What is the standard deviation? 35. You guys can't see it. Standard deviation 35. What is the sample size? 40. What is the percent confidence? 95. And how many decimals? 1 decimal. And then we get the answer currently on the screen. I hate that it does that with the graphics. It gets mad at the size of it. There it is right there. Let's look at that chapter 14 one. Clarissa, you got it. We'll end office hours with that one. Let's do it. What assumptions have you made? Oh, we did this one earlier, so we're good. Hot dog question is in here. Let's hop to space. Let's go grab... Wrong button. Okay, let's take a look. Chapter 14. Okay. Hop over to the main screen. And I believe this is the one. Have you gone over, suppose we were making a 95% confidence with a population mean from a sample size of 15. What degrees of freedom should we use? So the degrees of freedom for a one sample t, what is the formula, Clarissa, for the degrees of freedom for the one sample t? What is the formula for the degrees of freedom for the one sample t? So when we have a one sample t, what is the formula for the degrees of freedom? For the one sample t, the formula for the degrees of freedom will always be what? So think like one sample t. And the degrees of freedom, n-1. Yep. So what do you think the answer is? So what degrees of freedom will there be? If the sample size is 15, then what will be the degrees of freedom? You got it. Great job, Clarissa. Excellent work. Great job. Excellent work. So that's like when you get that one, you're like, yeah. Degrees of freedom for one sample t, n-1. Boom. 15 sample size, 14 degrees of freedom. Excellent work right there. Hop over here. Awesome work. I know, no, that's the thing. I knew you could get it. I knew it was like, once you see it, you're like, oh, 15 sample size, 14 degrees of freedom. Got it. That's what we try to do. We just practice it. You're welcome, Clarissa. Excellent work. It's like once you see it, you're like, I got it. Just practicing. Awesome. Awesome. Well, with that, everybody, we will end office hours. We'll be back later. And with that, I will see everyone soon. But bye for now, everyone. Bye.